Next, we are going to look at some special applications of exponential functions. We're going to talk about several different types of growth and decay. The first is simple growth by flat percentage. We have four different values that we are looking at when we deal with a problem like this. The formula for growth by percentage is A equals P times 1 plus R to the T power. And A is going to be the amount after T years. P, which stands for principal, is the original amount R is our interest rate, and T is time. So, using basic growth by percentage, let's say we invested $5,000 at 3% per year. So if we invest $5,000 at a rate of 3% per year, then the amount that we have after, say, 5 years is going to be calculated, right? So that would be A of 5 would be the $5,000 that we started with. So that would be 5,000, that's our principal, times 1 plus 0.03 to the 5th power. So after 5 years, we plug that into our calculator, and that's what I'm doing off screen. I hate doing anything off screen, but there we go. Let's go. We've got 5,000, open parentheses, 1 plus 0.03 to the 5th. And so after 5 years, we have $5,796.37. Now, that's if we compound, meaning that's if we get interest on that one time each year. But when we take a loan out from the bank, or when we utilize or we invest money, the investments don't just happen one time per year. The number of times that you compound, the number of times you get interest on something, can really be any number. And in using that, we're going to use a slightly different formula for compound interest. So our compound interest is A equals P times 1 plus R over N to the NT power, where A is the amount at time t, just like it was in our previous formula. R is the rate that we get per year. N is the number of times interest is paid per year. So instead of getting the interest paid one time per year, you are going to actually get that interest multiple times, but you get only a percentage of it. And we'll see how that works in just a second. And then T is still time in years. So just remember that when we only did it once per year, we did $5,000 at 3%. Once per year, we got $5,796.37. So let's see what happens if we actually compound that interest more frequently. So again, we will still look at that same $5,000 at 3% for 5 years. But let's look at a couple of different examples where n equals 2, n equals 12, and n equals 365. So, in other words, we're going to look at what happens if we compound the interest every 6 months. So that would be n equals 2. In 1 year, you have 2 6-month periods. So in that case, we would have 5,000 times 1 plus 0.03 over 2 to the 2t power. Now notice what's happening. Our percentage, instead of getting 3%, we're getting 1.5%. But we're getting 1.5% twice per year. So that first time you get the 1.5%, it's the $5,000. But the second time you get the 1.5%, you've got that little bit extra that you got off of it the first time. So since we are doing it 5 times instead of 2 to t, we're going to go 2 times 5. So I'm going to plug that in my calculator. And we get $5,802.70. So notice the amount of money that we got after a 5-year period, though it's not an extreme amount, just by getting interest 2 times each year instead of once each year, we went up by about $6. Let's do that same idea for 12. So we're going to have that same $5,000. We have 0.03% again, but this time we are going to get that divided by 12. So in the 1-year period, each year you're going to have 12 different times where you collect a little bit of interest. And notice, over a 5-year period, we're going to have 12 times 5. That's a total of 60 compounds. And so we get $5,808.08. So again, by compounding a total of 12 times, we ended up getting another $6 on our investment. Let's finally look at what happens when we go 365 times. So plugging 365 in for n, we have 5,000 times 1 plus 0.03 over 365 times 365 times 5 power. So now we're getting very little percentage, but we're getting a little tiny percentage a whole lot of times. And so by doing that, we get $5,809.14. So we did not get an extremely whole lot amount more, but by what we can see here is the more times we compound, the larger the amount of kickback we get off of our investments, or the more amount that you have to pay the bank if it was a loan or something. So that leads us to our next formula, which is the formula for continuously compounded things. In order to understand the idea of continuously compounded values, we got to introduce a new number. And that new number is E. And E is the most important number in the universe. It is used in radioactive growth. Radioactive decay. It is used in finding, when you do carbon dating. It's used in finance when you're compounding continuously. E is the most important number that there is. And it's like pi. It is an irrational number. E is defined as the limit as n approaches infinity of 1 plus 1 over n to the nth power. You do not have to remember that. E is approximately 2.718. 281828 goes on forever. But E is about 2.71. The good thing is, on your handy dandy calculator, you have two different places where you can use E. E is, if you look here, E is, the E that we're looking for is above the division sign as an E, and if you look at this ln key, there's an e to the x. So if I hit second ln, I get e to the first power. There's that 2.71 number, right? And that's using that key right there, where it says ln, and then you can see in blue it says e to the x. And that's how you use e. Now, why we need to know e is this. If we want to compound continuously, meaning we're not compounding once a day, we're not compounding once a month, we're not compounding once a year, we are compounding continuously. You are constantly, 100%, always in a state of getting interest, of decomposition, of growth. It's called continuous compounding, and it uses a formula that's A equals P e to the RT. Now, we've already seen the A, the P, the R, the T as variables, and now we also have that E value. Let's take our $5,000 using this A equals PE to the RT idea. So if we're looking at 5,000 at 3% again for 5 years, we just plug that in as 5,000 e to the 0.03 times 5. And we get 5,809.17, which is very similar to what we got at 365, but that is the absolute best you can do. So in a nutshell, that is how to work with the special applications. You have an applications worksheet that you can do. If you have any questions, let me know. Enjoy your mathing, and I'll see you later.